I'd like to start by thanking the organisers for the opportunity to give this talk. And this is going to be work following on from Justin's talk just now. This is going to be talking about positive feedback in galaxy formation with SPHS, connecting small to large scales. So I don't need to go over the details on SPHS because Justin's just outlined that. So hopefully what I'm going to be able to do is convince you that using SPHS for these sorts of simulations opens up all sorts of exciting possibilities for new science. And so this is work done with Justin, with Chris Power at University of Western Australia, and with my student in Zurich. So first, a bit of motivation. We know that the star formation history of the observable universe as a whole has been declining rapidly since about a redshift of 2. This is a factor of 10 here. But we also know that in disk galaxies like the Milky Way, this slope is much flatter in terms of the star formation rate. And this is a plot of the star formation rate in the solar neighborhood, which only declines by about a factor of 2 over a very large range in time, basically a Hubble time. And this requires that the disk is constantly replenished with cold gas that is able to form stars at a rate of about a solar mass per year. A promising source for this is the presence of, possible presence of an extragalactic hot corona, seen here in an artist's impression, which typically is expected to extend beyond about 100 kiloparsecs. It's quite hot, has a temperature of 10 to the 6 Kelvin, mass of a few times 10 to the 10 solar masses. And there's a variety of evidence for this in terms of detection. There's X-ray emission from hot gas. There's absorption lines to quasars. There's dispersion measures of pulsars in the LMC. Indirect evidence in the form of galactic baryon deficiency and RAM pressure stripping of the Magellanic Stream and satellite galaxies. Now, in general, models, semi-analytic models of galaxy formation like to basically imply a form of self-regulation whereby the galaxy is a reservoir of gas, cold gas, and the inflow and outflow is set by a thermostat-like mechanism. We want to try and answer the specifics of these in simulations to try and figure out what's going on. And this is where I make a plug for what are called toy simulations, which are a little bit different from some of the all the bells and whistles, amazingly high resolution, amazingly pretty simulations that we've seen this week. Obviously, the two have to complement each other, but I do think that sometimes you can learn quite a lot from these smaller dedicated simulations as long as you make sure that you get as much right as you possibly can. And this is one of the simulations I'm going to do now with SPHS. We already know what that is, Justin explained. He also explained that there were lots of other flavors of these Lagrangian algorithms that come out in the last few years. And I'm going to make lots of comparisons with SPH. So I need to be very careful with my definition so as not to be unfair to any existing codes. When I talk about SPH, I'm referring to classic SPH, which is basically of the form of Gadget 2 when it was released. So here's my setup for my simulation. It's a cooling hot gaseous halo, as per the Kaufman papers, which forms a Milky Way at the center. This is approximately equivalent to a late smooth accretion mode. And here are my parameters. This is the density profile, it's a Dana-McLaughlin model. We implement hydrostatic equilibrium initially for the gas, which is then allowed to cool, has a rotation profile such that the angular momentum goes as R. These are my subgrid parameters. First, I should say that the initial conditions are fully relaxed to make sure there's no spurious noise, because that's quite important. We have a cooling floor of 100 Kelvin and a polytropic adaptive floor which resolves the gene's mass at all times. We have a fixed density threshold above which stars are allowed to form. This density threshold is about 100 atoms per cubic centimeter. And so we're using approximately a few times 10 to the 4 solar masses in our gas particles. So here's a movie. SPHS on the left, SPH on the right. This is the opposite way around to what Justin showed, I'm sorry, just to confuse you. initially you see it's very similar, but already we see that the walls of the bubbles from the supernovae are more mixed in SPHS. And that's a herald of what comes now, which is the formation of many hundreds of dense clumps in SPH, which are not there in SPHS. What we see in SPHS is the formation of filaments. And the bottom panels here are a zoom in to the central region where you can really see the differences in the buildup of the galaxy. One is formed through the scattering of many of these dense clumps, and the other is formed through these nearly radial directed filaments that come in and feed the disk. And this is very interesting. We know from some papers by James Binney and by Young et al. That you would not expect a thermal instability in ambient gas, either in the linear or nonlinear regime, to form these clumps in these sorts of situations. So why are they there? Well, this is a plot similar to one of the ones that Justin showed, which basically explains that the main problem is that when you get multi-valued pressures at the boundaries between two phases of fluid, you drive these pressure spikes, which not only give you an artificial surface tension, protecting the gas from mixing, but they also drive pressure waves, spurious pressure waves, into other areas of the fluid. And that was an idealized simulation from the SPHS paper, but here's this actually happening in the simulations I just showed. The spikes here we see are the dense clumps that form in SPH. This is the ambient pressure in the medium. And we see at the boundary of the clumps, we have these dips in the pressure, these pressure spikes, which cause the problems. So this is in terms of the protection of each clump from artificial surface tension in terms of being mixed, but what about the actual formation of them? Well, here I have basically a particle by particle investigation into how this happens, which is that I've got a clump in SPH, one of the largest clumps that forms in SPH, one of the largest spurious clumps, and this comes together from three regions of gas. What happens is I'm going to run the movie. This is entropy on the bottom and pressure on the top, and it's going to stop at the point where the density gets smoothed. Okay, so any peak in the density gets smoothed away. What you see in SPH is that the entropy does not, and this is only a few particles, but we'll see later it makes a huge amount of difference. When the entropy is not smoothed away, you get a corresponding dip in the pressure, which is what brings the gas in and forms the clump. When I run this in SPHS, okay, here we go. This is pretty slow. Okay, if I run this in SPHS, exactly the same setup, but you see at the moment where the density smooths away, so does the entropy, which means there's no dip in the pressure. And this is what the two situations form in SPH. You have the clump. In SPHS, you have the filament, and these are from exactly the same identical condition. So I want to go back to this plot, and I want to look in more detail at the differences between the two, because they actually give some quite striking morphological differences in terms of the buildup of the galaxy, which, as I've said, is through the scattering of many clumps in this case and filaments in this case. We know that a common problem in galaxy formation simulations is that the disks tend to be underdominant with respect to the bulges, which tend to be too large. And we see that here in the plot of JZ over JC. This is the signal from the bulge, which is very dominant in SPH. And in SPHS, we see that we've enhanced the disk signal significantly, simply by this different mode of formation as the disk builds up. So I think this is a very promising mode of formation, this particular mode via filaments, so I want to investigate that in more detail. So here's the high resolution version, where you see that the filaments break up into lots of little clumps. And it turns out these filaments are very, very good at feeding the disk. This is the accretion rate in the red dotted, I hope you can see that up here, which shows that the accretion rate through the filaments onto the disk is about a solar mass per year, going down to about 0.1 solar mass per year over a gigayear. We also see that the star formation rate in the disk is similar and follows the same form, which implies a form of self-regulation, which is particularly interesting. What I've done here is I've attempted to characterize these filaments in terms of the angular momentum distribution, particularly the low angular momentum tail, which obviously has implications for feeding the galaxy disk and for feeding, ultimately, the black hole at the center of the galaxy. So I've isolated a filament, and I've plotted the angular momentum histogram, which is here. If I zoom in, we can describe this quite nicely analytically by positing that it is due to these supernovae-driven filaments simply into two power laws that depend on the trajectory that the gas is condensing along. When you have a curved trajectory, such as shown here, then you have a power law of j to the 1.1, and a straighter trajectory gives you a steeper power law of 2.2, and this obviously has implications for the growth of the galaxy in terms of the low angular momentum material. And then my final movie in this section, I want to show that these filaments are particularly good at getting gas from large scales down to small scales. What I've shown here are particles, gas particles, color-coded according to where they end up by 2 gigayears. Okay? So these are in radial shells. The blue particles are those that end up within the inner kiloparsec. And you see that they already start out, in the initial condition, out to 40 or 50 kiloparsecs. If I run the movie, what happens is we have an initial set of blast wave, which tends to make all of these particles lose memory of their initial conditions. And then when they come back, you see the blue particles have reached very large distances. You have these colliding flows, which create the filament at the same time as another burst of supernovae go off to condense the filament, cause it to feed the disk. And what happens is these filaments can bring particles from these distances all the way into the center, which we see hopefully at the end there. Okay, so just to summarize this new mode of feeding, which I'm terming supernovae-driven accretion flow, it's a fragmenting filament, and this is actually quite similar to the breakup of the cold mode cosmological streams, although on different scales, on different temperatures, and obviously with a different progenitor, supernovae, rather than the underlying dark matter web. And it's a form of positive feedback, because supernovae give rise to gas flows, which actually come back, feed the disk, and actually fuel further star formation. And these filaments can be very efficient at bringing gas from large scales down to small scales. All right, in the last few minutes, I'm actually going to cheat and move on to something a little different, something which is very, very new, in the sense that I've actually been doing this the last few days, both in terms of the simulations and the analysis. This is SPHS, the first SPHS simulations in a cosmological setting. Okay, so this is hot off the press, and I should establish very, very preliminary. This is my animation slide. I'll just very, very quickly go through how this is set up. You can ask me at the end if you're interested. Basically, we resimulate with gas at Z of 4, a Z of 4 cluster, which is identified with the friends of friends algorithm. It's very, very low resolution, I should say. So we're not going to see any of the beautiful structure that we've seen in some of the very impressive simulations this week. Our gas mass is about 10 to the 7 solar masses, but already we see some interesting things. Subgrid physics, I have radiative cooling down to 10 Kelvin, star formation threshold of 5 atoms per cubic centimeter, feedback from supernovae 2 and 1A, and injection of thermal energy, metals, and mass as per the Agora paper. And of course, in SPHS, all of these quantities of the fluid, they actually mix through diffusion. So here's the initial resimulation regions. This is what it evolves to. What I'm really interested in, obviously, is the comparison between SPHS and SPH, which I can see much more easily if I overlay them. And if I just flick through, oops, that was the wrong thing. Okay, if I just flick through, you can see that the main differences are the presence of a stronger CGM in the SPHS simulation and the presence of more small-scale structure in the SPH. But there are obviously a lot of similarities. The underlying structure is the same. There's halos which match up in both plots, but there's also halos which don't. And these typically are the ones that in SPHS are stripped away. What I want to do is zoom in now to the central region where we see something interesting. There's actually more diffuse structures in the SPH simulation than there is in the SPHS, but this makes sense, thanks, because in the SPHS, only the dense stuff can get into the center. Anything else gets stripped and mixed away by the diffusion. And what I want to look at now is a galaxy, a proto-galaxy, that is the same in both, or it's present in both simulations, but is already different. So if I zoom in and look at that, we see that in the SPHS case, the disk is more extended, both in the gas and in the stars, whilst in the SPH case, we see a more compact disk and more of a spheroid in the stars, although we do see a relatively strong warp in the SPH case as well. And this is particularly interesting because this simulation is so low resolution that the formation mechanism that I discussed with my toy simulation of cooling halos really isn't happening here. We did see some extra blobs, right, but they were very few, and it's very unlikely they would have been able to contribute to the formation of this galaxy. So why are the two different in this case? So I'm going to zoom into the galaxy again. This is an SPHS, and the reason is one aspect of SPHS which I haven't really mentioned, which is the improvement in the artificial viscosity parameter. This is alpha, shown here in colored contours. In SPH, this is fixed at 1, very high, so all of this would be white. This has often led to people describing SPH simulations as actually modeling honey rather than actually modeling gas, particularly at low resolution. What you see here in SPHS, that the viscosity can drop by a factor of 10 to about 30 in the galaxy that's forming. This is the switch. I'm not going to go into any detail on that, but the important point is that the viscosity is proportional to this alpha parameter, and the mass accretion rate through viscous angular momentum, so numerical viscous angular momentum, is also proportional to this alpha parameter, which means that a factor of 10 to 30 in the alpha improvement gives you also a factor of 10 to 30 less spurious numerical loss of angular momentum in the galactic disk, which means that it can stay in the right sort of morphology, can stay more disky for longer rather than draining away, becoming more compact. Okay, so these are my conclusions. We've established both in Justin's talk and this one that SPHS corrects for some fundamental limitations in SPH, mostly relating to mixing, but also to force accuracy. And we've seen that it eliminates spurious cold clumps. I think that's the key word in SPH simulations. This allows us to investigate a new mode of disk feeding via this supernova-driven accretion flow. And some first very preliminary results from the cosmological simulations do suggest promising behavior, but I really need to do this at high resolution and investigate it much, much more. Okay.
Monsieur?
Alex, in modern SPH codes, everybody uses a Balsara switch that should already reduce the viscosity, so it shouldn't be all white, as you say.
Yeah, sure. Yeah, that's true. If you use the Balsara switch, okay, and this is not classic SPH, that doesn't have the switches, but Balsara switch is one of the improvements to the SPH algorithm, absolutely.
Did you check?
You gave it.
I haven't yet, no, but that's definitely something I should do. Yeah. So, did you want to say?
I just want to clarify, just to not confuse people. Classic SPH does have the Balsara switch, but the Balsara switch in SPHS is a second order accurate one. So they both have some kind of a Balsara switch.
Any questions?
I think that the spurious
Well, I think, I mean, it doesn't matter about what resolution you have it, right? If you have a viscosity, or a numerical viscosity will give you numerical angular momentum transport, right? So if you can reduce that viscosity by a factor of 10, you reduce your numerical angular momentum transport by a factor of 10 as well. I mean, it gets better with high resolution, but the comparison is still the same. The comparison is still the same because it's still proportional, right? But I should make that plot at high resolution and see the improvement. I think it might be even better, actually.